Welcome back to integrated circuit course lecture series. Okay. I am Punit Kumar Mishra, assistant professor, EC department, GLB ITM, Greater Noida. Today we discuss about the CMOS logic design with respect to sequential circuit. Sequential circuit is a circuit which is basically behaves as a memory element and basically work on a bistability principle. Okay. So, bistability principle means in analog electronics we consider a bistable multivibrator, and simply the basic concept of bistability, this will be the number of even inverter. Number of even inverter means 2, 4, 6, 8 connected in a positive feedback loop. These are connected in a positive feedback loop. So, if you consider this circuit, here inverter, this is the inverter 1 and this is inverter 2, and if you give the input 0, this is 0, this will be the 1, output of the first inverter is 1, output of second inverter is 0, it will be 0, 1, 0. Okay. Next time if you give the input 1, it will be output of first inverter is 0, output of second inverter is 1, 1, 0, 1. So, it can be hold either logic 0 or logic 1. Basically, this is behave as a memory element. Okay. And it has the two stable state, logic 0 and logic 1. Okay. So, these are the basic of flip flop or a latch. Here the inverter of first output of first inverter connected to input of second inverter. Okay. And in output of second inverter connected to input of first inverter. This is the latch. This circuit will call latch. And finally, we replace the inverter with a universal gate such as NAND and NOR, and according to our mechanism or our input or output, it can be defined as a SR latch, D latch, or a clocked SR flip flop, JK flip flop, T flip flop. Okay. So, first we consider the SR latch using NOR gate. The SR latch is basically cross coupled of two NOR gate with the input S as a set and R as a reset, and two complementary output Q and Q bar. Okay. So, here consider 0 0. If you take the input 0 0, the output follow the previous state. For example, if you consider Q is 1 previously and Q bar is 1, Q definitely Q will be 0, and we 0 here consider, we given the S equal to 0. So, 0 0 at NOR gate it come 1. Okay. And this 1 will reflect here at the input of first NOR gate, this one the second first NOR gate, and 1 0 give the 0. Okay. So, it follow the previous state. So, 0 0 it give the previous state. Okay. And it is called the hold operation. Okay. This is called the hold operation or previous state. 0 1. Okay. In case of 0 1, if you put the 0 1 output Q as a consider as a 0, so this will be the called the reset state. And for 1 0 output will be 1, Q bar will be 0, it reflect as this is the set state. Okay. This is called the set state. And 1 1, what about the 1 1? Okay. In the NOR gate table, if you consider the truth table of a NOR gate, if any input is 1, output is definitely 0. So, if you consider here R is 1, S is 1, R is 1 and S is 1, definitely Q will be 0, Q bar will be 0, and both are complementary. Q and Q bar is complementary, and same time both give the same value, that is the logic 0, it is the invalid state, undefined state. So, for 1 1 it defined as, for 1 1 invalid state. One basic concept why SR flip flop give the invalid state, or with respect to NOR or a NAND gate. If logic defined as a enable or a disable input for a NAND or a NOR gate, for example, logic 1 is a disable input for a NOR gate. Logic 1 is a disable input for a NOR gate. So, if both input are 1, so for a NOR gate both give the disable input, output is definitely invalid. In case of the NAND gate, suppose we design the SR latch with the NAND gate. In case of a NAND gate, if you give the 0 0, logic 0 is the disable input for a NAND gate. So, in that case SR latch with the NAND gate give the invalid state for input 0 0. Here is our motive is designed to CMOS implementation of this circuit. How can design? So, here is simply put Q. If you solve for a NOR gate, we define the separately. Here you consider the first NOR gate, upper side, this is the 1, this will be the 2. Okay. This will be the R, this is the 1, and this is the Q bar, input Q bar, and this will be the Q. Okay. So, Q will come out R plus Q bar whole bar. Okay. This is the first NOR gate in previous. Separately, we can separate the both NOR gate 1 and 2, and second NOR gate. In case of second NOR gate, this is the input S. This consider as a Q, input S, and this is the Q bar. Output will be S plus Q whole bar. Okay. Now we design separately these two Boolean function Q and Q bar. Okay. So, first let us suppose that design for a Q bar. Okay. So, in Q bar S plus Q, this is the Q, this is the S, and both are connected with the OR operation to NMOS connected in parallel, NMOS connected in parallel, S and Q. For a PMOS, if S and Q connected parallel in a NMOS combination, definitely they are connected in series in PMOS. So, this is the S and this will be the Q, and output is Q bar. Output is Q bar. This is the first for a second NOR gate. Consider the second NOR gate and first NOR gate here. First NOR gate say R Q equal to R plus Q bar. So, this is the R and this will be the Q bar connected in series parallel or a shunt manner. Okay. In PMOS they are connected in a series manner. So, this will be the R, this is the Q bar, and output is Q. Okay. Finally, Q and Q bar not defined as a input. Okay. So, output of first is Q bar and it connected to input of second input of our second design. Second design means for NOR gate first. Okay. For NOR gate first. So, Q bar connected to as a input for a NOR gate first, and Q is output of a first NOR gate, it connected to the input for second NOR gate. Okay. Here we try to separate design this one. Okay. First design, this is the S, this will be Q, second NOR gate, and for a first NOR gate, the R, this will be the Q bar, the R and Q bar. Okay. This is the pull down network, Q and Q bar. Now this is the VDD, okay, for PMOS. This will be the S, this is the Q, and output is our Q bar. Similar, here this is the VDD, this will be the R, the PMOS with the bubble sign here. Okay. This is the Q bar, and output is Q. This is the separate, this for NOR gate 1, and this is the for NOR gate 1. This is for NOR gate 2, 1, and this is for NOR gate 2. NOR gate 2. Okay. This first define the separately, and where is the Q? Q bar is the output of our first design. Okay. This is the these are the symmetry to each other. Okay. Then Q bar connected to input of this Q bar. This is the Q bar, and output of first NOR gate or a second design is the Q, and it connected to the Q and also here. Okay. So these are the CMOS logic implementation of SR latch using the NOR gate. Okay. Using the NAND gate is similar to NOR gate. This is the truth table, set reset output. Okay. Here 1 1 0 no change in the previous state, and 0 0 is invalid state. We discuss about, because the 0 0 is a disable input for NAND gate, so it gave the invalid state. Same manner 1 2, it is separate one, it is separate the one NAND gate and NAND gate 2 separately, and define the Boolean function for both NAND gate in terms of S, R, Q and Q bar. Okay, and try to design the CMOS logic implementation. Okay. CMOS logic implementation as similar manner. Okay. If you now next clock the SR latch, one is the buffer circuit. It is the combination of basically the buffer. These two AND gate combination work as a buffer, okay, and this is the latch. This will be the latch, okay, and this will be the as a buffer or as a steering circuit, okay. And purpose of this NAND gate input side two NAND gate combination is synchronize the data with the clock signal. Data is set and reset, and clock is try to synchronize this. This is the buffer. Why it called buffer? Because with the high enable input clock is 1, if R is 0 output is 0. Here 1 if the input is 1 output is 1, okay. Output is same as the input if clock is enabled. Okay. Yeah, in case of design, it takes the maximum number of transistor because it combination of two NOR gate and two AND gate. So how can we design this? So we take the Boolean function here R dot CK or CLK clock, CK as a clock, okay, and here is the Q bar. This is considered as a Q bar, okay. This will be the Q bar. So basically QT as a Q, it will come R dot clock plus Q bar whole bar, okay. In same as a same manner, if the AND gate this first, this will be the second AND gate give the S dot CK as a clock signal, okay, and here is the Q as a input for a NOR gate 2. Q bar will come S CK plus Q whole bar, okay. This will come, and we forget this gate representation for a design of transistor level, okay. For a design at a transistor level, we forget the gate level representation. We only memorize these two Boolean function and try to design these two Boolean function. Q is equal to R dot clock plus Q bar whole bar, and Q bar equal to S dot clock plus Q and Q bar, okay. So these are the representation, and if you try to design, we get in previous slide, okay, Q R dot CK Q bar whole bar, okay, and Q bar S dot CK plus Q whole bar, okay. So we try to design this one here, this is here. S dot CK or same as erase it. R dot CK, so R and CK in a series combination or CK, okay, plus Q bar, this is the Q bar, R CK Q bar, okay, and for PMOS this is the VDD, this is the PMOS CK CK, and this will be the R, the parallel combination, this will be the Q bar, output is Q. Okay. Same here, we take the mirror image and change the R with S and Q bar to Q, the clock remains as same. So, this is the VDD. Okay. Take here the same CK, this will be the R, sorry R, it is not R, it will be S, Q, and here is S, this is the CK, this will be the Q, and this is the ground, output is Q bar. Okay. So, finally, we match Q with the Q bar, this is the output, and this for input for second one, here is Q bar, so we connect this, and this is the Q, also Q. So, this is the CMOS logic implementation of the clocked SR latch. Now, the D flip flop we mostly use in a VLSI circuit, not a SR, clocked SR or a JK or a T, because it takes the large area, because number of transistor is required more during the CMOS logic implementation. So, we concentrate on a D flip flop, and D flip flop is also defined as a transparent flip flop, because the output Q is equal to input D, and D flip flop is as a gate label, representation. D flip flop is simply obtained by putting S equal to D and R equal to D bar in a clocked SR latch or a flip flop. Okay. So, basic CMOS logic implementation of this circuit, and this two switch is called transmission gate TG1, and this is the TG2. Okay. If we go for a truth table of CMOS D flip flop, let us suppose that this is the clock CLK or a CK. We consider CK as a clock D. Okay, this is the Q. Okay, clock is 0, Q n plus 1. This is the Q, maybe don't care. Okay, so it follow the previous state. Okay, if clock is 1 1 0 0, so output is 0 1. Okay, so this is the hold operation, and this one the transparent. Transparent operation where Q is equal to D. Okay. So, how it can design with this basic concept of this? So, we say that a CMOS memory is designed with a number of even inverter in a positive feedback loop. So, we consider the two inverter, okay, inverter 1, inverter 2, and here give a two switch. Okay, here one switch here and one switch here. It is the output considered as a key Q and input is D. If switch is on, for example, this is the switch 1 and this is the switch 2. Okay, if switch 1 is on, for example, switch 1 is on, this is the on, and switch 2 is off, this will be the off. In this case the output of first inverter is D bar and output of second inverter is D, and Q will become as D. Okay. This is the transparent operation. Second possibility, this is the case first where Q will become as a D. Now the second possibility, second possibility will come when case 2 switch 1 is off, okay, and switch 2 is on. Switch 2 is on, it says that it is off and this will be on. Okay. It means it hold the previous state. The circuit will hold previous state. What suppose that if here is 1, previously 1, it is stored previously 1, this is 0, this will be 1, so it hold Qn plus 1 equal to 1. Okay. This concept will apply to design of CMOS implementation of D flip-flop, because we need a less minimum number of transistor for designing of a flip-flop. So here the switch will design with the transmission gate. Transmission gate is basically two parallel combination of one PMOS and one MOS, and both are operated with the complementary input. Okay. Here also see TG1, one is CK and second one CK bar, TG2 CK bar and CK. And inverter in a bistability principle, both our inverter are designed with the CMOS, that is the combination of PMOS and NMOS. Okay. The inverter will replace with the this is the first inverter and this is the second inverter. Okay. So if clock is high, case first consider, so when switch 1 is on, okay, it means for case first CLK equal to logic 1. CLK equal to logic 1, this is the logic 1, CLK bar is 0, this is on, this will be on. Okay. CLK is 1, this is off, CLK bar is 0, this will be the off, and in this case Q equal to D. This is the first case. Okay. This is the operation of D flip-flop. In operation of D flip-flop, we consider the two cases. Case first when clock is 1 and case 2 when clock is 0. Okay. Now case 2 when clock equal to logic 0. Okay. When clock equal to, this is the TG1, this will be the TG2, clock equal to 0, this will be 0, this is the 1, this goes to off state, NMOS also off state, the clock bar is 1, okay, this is the on state, this will be the on state. Okay. So we say that TG1 off, TG2 on, an equivalent circuit is look like D is the open switch. Okay. This is the 2 inverter, CMOS inverter, we represent at gate level, and this is the closed switch, this will be on, this is the off, okay, and Qn plus 1 is equal to Qn. It hold the previous state. This is the simplest method of design of D flip flop using the CMOS logic. It required only 8 transistor. If you go with the SR flip flop or a JK flip flop, they require the maximum number of transistor, and if complexity is increases, definitely speed will be reduced. Thank you for listening my lecture.